In item 5, we are looking at a production of shoes, and in this case, the weight of one shoe. It is drawn from a normal distribution, or I should say it's modeled from a normal distribution. It has a mean of 12 ounces, standard deviation of 0.5. And in part A, we're just asked a simple calculation of what's the likelihood that the shoe's weight is greater than 13 ounces. Why would we care? That might be where the tolerance level has been set in the quality control process. And so that's the same thing, of course, by the way, as 1 minus the probability that the weight is less than or equal to 13. And since the weight is modeled with a normal distribution, we can define instead now z equaling to w minus the mean of w divided by the standard deviation, or w minus 12 over 0.5. That'd be the same thing as 2w minus 24 ultimately. And so if we are then looking at probability of w being greater than or less than or equal to 13, that is, that's the same thing that z evaluated at w equal to 13 of then 2 times 13 minus 24, or 2 for z. That's key, because what that just told us is that the probability that we want is 1 minus the cumulative normal distribution evaluated at z equal to 2. And on that bell curve, then we're looking at then all this probability area or mass. Oops. That's the CDF at z equal to 2. What we really want is the area that's out here in the tails. Hence why we're doing the 1 minus business. So there, all we have to do is go into the cumulative standard normal table. We have a positive z value of 2.00, so 2.0, and add 00 to it, and we get then the 0.9772 as our answer. And so that, or well, partial answer. So the probability that z is greater than 2 is 1 minus the probability that z is not equal to 2, but less than or equal to 2. And so it's 1 minus 0.9772 equals 0.0228 for our answer. Now we could have actually looked this up as the whole thing as phi of minus 2. We're taking advantage that we can flip-flop over here and we have a symmetric distribution. So that little piece is the same as that tail area if that's at minus 2. Another way to do it. Right? Then we're asked to say if the standard deviation of the weight in order, we're trying to find a standard deviation of the weight in order that there's a 99% chance that a single shoe weighs less than 13 ounces. So in part B, what z goes with phi of z equaling to 0.999. Right? And there, when you look that one up in the table, although there's a couple of different places that you could end up, you've got a 0.999 here, a 0.999 there, 0.9990 on the next one. Then there's obviously a fifth digit at work here. This one's in the middle, so I choose 3.0 in this last column, which is 0.09. Right, so we want z equal to 3.09. And we're trying to solve then, if that's the case, we've got w evaluated at 13. Its mean is still 12, but we don't know sigma w. That's what we're trying to find, and that's where then you'll be able to determine that the standard deviation that goes along with the 99% chance is 0.323. Then in part C, we're asked about a pair of shoes. And there, and really parts C and D are linked together, so we can do these together. And so now we've got 2 shoes, and the total weight, y, equals the sum of the individual ones, assuming that they are independent identically distributed. Right? So the expected value of y, this is just a expected value of a linear function, so therefore that's the sum of the individual expected values, and since those are the same, that would be 2 times 12, or 24 ounces. Now the variance, though, is a little more tricky, because with the variance, now you've got to look at the variance of a sum. And the variance of a sum is going to be the sum of the individual variances. All right, so wait a minute, let's work this out. 1 plus that, and that is going to be the variance of the individual one plus the variance of the second one. And then we've got to get in there 2 times the covariance of these 2. Right, so let's flesh this out just a little bit more, tease it out. We've got the variance of the one plus the variance of the second, plus, and the covariance can be written as 2 times the correlation coefficient times the individual standard deviations. And so if we have independence, then rho equals 0. And so for part C, then our new variance is equal to the sum of these individual ones. That would be 0.5 squared plus 0.5 squared. And so that's just 2 times 0.5, 2 times 0.25, or 1 over 4. And that would equal 1/2. Didn't do something right. Oh no, fine. Got myself confused there. Because then I want the standard deviation, which is the square root of that. That's what I was thinking I didn't do right. I knew that was the final number that I wanted. And then to answer part D, if the 2 shoes are positively correlated, that's going to increase the total variance, but it has no influence on the mean at all.